Good afternoon, I'm Zara, and today I'm presenting our work, Decoding Brain Age, a self-supervised graph neural network framework for EEG analysis. This research was conducted with the National Research Council of Canada, the University of Waterloo, Simon Fraser University, and Fraser Health Authority. Our goal was to enhance brain age prediction using a combination of self-supervised learning and graph neural networks to overcome limitations in traditional machine learning methods. EEG recordings are valuable for capturing neurophysiological states, with brain age prediction providing key insights into brain health. To scale this diagnostic technique, we propose a computer-aided system using self-supervised learning and graph neural networks for EEG analysis. Self-supervised learning reduces the need for fully labeled data by pre-training models on large unlabeled EEG datasets. We tackle temporal spatial feature learning challenges with graph neural networks, employing graph-based representations of EEG signals to depict the brain's interconnectedness and extract meaningful features. Furthermore, we enhance the explainability of brain age prediction by visualizing channel-wise maps, highlighting critical EEG channels influencing the model's decisions. As I said before, EEG recordings have become a valuable tool in clinical settings for capturing neurophysiological states and enhancing diagnostic accuracy. Specifically, EEG-based brain age prediction offers insights into brain health by providing a comparative measure of biological versus predicted brain age. The comparison enables clinicians to assess patient brain health, as discrepancies could signal declines in mental well-being associated with neurological diseases or degeneration. Detecting significant deviations in predicted age can serve as a biomarker for such conditions, potentially facilitating early interventions. To scale this technique, developing computer-aided technologies for efficient information extraction is crucial. While AI has shown significant utility in digital healthcare, traditional supervised models, particularly deep learning models, face limitations due to their reliance on accurately labeled data. Additionally, it presents a challenge to conduct feature learning from biological signals. That's why we propose a self-supervised EEG GNN framework to reduce the need for fully labeled data in brain age prediction. SSL extracts meaningful representations from unlabeled data through pretext tasks. By leveraging SSL, models can be pre-trained on large-scaled unlabeled datasets to learn general features, and then fine-tuned on smaller labeled datasets downstream. This reduces dependency on extensive labeled data and enhances the model's ability to capture intrinsic EEG signal patterns, potentially improving brain age predictions. Effective temporal spectral feature learning is addressed using GNNs. Graph-based representation of EEG data illustrates the brain's interconnectedness in an interpretable manner. GNNs utilize the spatial structure within EEG recordings to extract features and identify patterns based on electrode interactions. Spectral GNNs represent EEG data in the frequency domain, and temporal information is integrated by combining the spectral GNNs with recurrent layers to process sequences of spectral representations over time. So our key contributions include that we introduced an SSL framework that integrates GNNs to predict brain age from EEG data, addressing the limitations of traditional supervised learning. We achieved the lowest mean absolute error compared to the other models that have been used on the dataset that we use. We performed an inclusion analysis to identify the most important EEG channels for brain age prediction, adding an explainability component to our approach. I'll briefly go over some related studies on EEG-based brain age prediction. So on other datasets, random forest regression and relevance vector machine have been used. These methods achieved an MAE of 1.22 years on children's EEG data. LSTM models achieved an MAE of 7.3 years. However, on our dataset, the following models have been tried. EEG-NET reached an MAE of 18.59 years, while a transformer model achieved 17.22 years. A generative AI approach was also tried, which used synthetic data and integrated that into the training set, and achieved an MAE of 6.271 years. However, none of these approaches use SSL for brain age prediction, This gap motivated our work to explore SSL in this domain. The dataset for this study consists of EEG data collected during routine clinical visits at 7 hospitals in British Columbia, Canada. To ensure uniform sampling frequency, raw EEG signals were extracted and resampled to a frequency of 200 Hz. The resampled EEG data undergoes random reflection and scaling to introduce variability and enhance model robustness. Graph-based neural networks capture spatial relationships between EEG channels through adjacency matrices. The dataset is split into training, validation, and test sets using a 64-16-20 ratio with 5-fold cross-validation. So we integrated SSL and GNNs for brain age prediction using a diffusion convolutional recurrent neural network. Here's how the approach works. So there's a graph representation. The EEG data is represented as a graph where nodes correspond to the EEG channels and edges represent weighted connections based on cross-correlation of signals. To introduce sparsity, we retain only the top 3 neighbors for each node. We use a DC RNN to capture both spatial and temporal characteristics of the EEG signals. This architecture allowed us to learn meaningful patterns from the interconnectedness of EEG data. So this slide illustrates the framework I just described. As you can see, the process begins with graph construction from the EEG data, followed by the application of the DC RNNs to learn both spatial and temporal features. The final output is the predicted brain age, which is compared to the ground truth during training. The GNN inputs are sets of graphs, each with nodes, edges, and node features. The EEG clip is represented as a graph where V denotes the set of nodes, E denotes the set of edges, and W is the adjacency matrix. The dynamics of the brain connectivity are captured by defining the edge weight W as the absolute value of the normalized cross-correlation between the pre-processed signals. Each graph G is associated with a label Y indicating its class. The goal of the GNN model is to learn a function that can predict the class Y given the input graph G. We leverage a pre-trained DC-RNN model, which employs a self-supervised pre-training strategy. This method predicts pre-processed EEG signals for the next time period, thereby enabling the model to learn task-agnostic representations. The dataset used for pre-training consists of a large collection of EEG recordings from the Temple University Hospital EEG seizure corpus, which includes both seizure and non-seizure data. The model is trained in a sequence-to-sequence manner with an encoder and decoder architecture, each comprising of several stacked DC grooves. The training objective is to minimize the mean absolute error between the true and predicted pre-processed EEG clips. This pre-training approach allows the model to effectively capture the spatiotemporal dependencies in EEG signals. For age prediction, we fine-tune the pre-trained DC-RNN model using our EEG dataset. The DC-RNN architecture captures the spatiotemporal dependencies in EEG data with 2 recurrent layers of 64 units each and a maximum diffusion step of 2. Gated recurral units within the diffusion convolutional framework effectively model complex EEG signal characteristics. We train the model with mean squared error, loss, and atom optimizer. Gradient clipping with the maximum norm of 1 ensured training stability. The model was trained over 80 epochs with batch processing, loss computation, and backpropagation for parameter updates. Our model outperformed other approaches on the same dataset. An MAE of 16.93 was achieved and was the lowest among the compared models. Root mean squared error was also the lowest compared to the other models. Our results suggest better generalization and reliability in predicting brain age from EEG data. To better understand the model's decisions, we conducted an inclusion analysis. In this technique, we systematically occlude or temporarily remove each EEG channel to observe its impact on the prediction accuracy. By doing this, we can measure how the absence of each channel influenced the model's ability to accurately predict brain age. Channels that caused a significant drop in accuracy when occluded were identified as critical for brain age prediction, while those with minimal impact were considered less influential. So why does this matter? It's essential to understand not only what the model predicts, but also why it makes those predictions. The results of our occlusion analysis provide deeper insights into the specific EEG channels that are most critical for the model's predictions, and has several key benefits. These include identifying critical brain regions, personalized diagnostics, trust and interpretability, and improving clinical decision-making. We generated graphical representations to show the contributions of different EEG channels for various age groups. These visualizations allowed us to see which channels were consistently influential across all ages and which ones were more critical to specific ages, such as 25 or 70 in this example. This approach helped us validate our model by demonstrating that its predictions aligned with known patterns. So our findings demonstrated that incorporating SSL with GNN significantly improved brain age prediction accuracy. The pre-training phase enabled the model to capture intrinsic EEG patterns effectively, even with limited labeled data for our task. The occlusion analysis not only validated the model's predictions, but provided a way to identify important EEG channels. In conclusion, we presented a self-supervised GNN framework, and our occlusion analysis added explainability component that can be used to further check and ensure trust with these models in the clinical setting. Thank you.